So our project was called Modelling with Data, but our interest was in the practice of statistics. Now, this is a term that Moore and McCabe first used in 1989, but our project sort of took it on quite a lot as a mode of inquiry for students. So underpinning what we're doing is what we call the practice of statistics. Now, Wild and Pfannkuch did a lot of research into looking at how statisticians work, and they published a framework for how statisticians work. And then the Gaze report, the American Guidelines for Assessment, Instruction, Statistics, Education, sort of took on board those ideas and made it less complex for schools. So the practice of statistics is just made up of these four elements. This is the way that we've interpreted it for our project. I do know there's other frameworks that have extra sections. The Gaze framework has 5 sections, not 4, but this is a simple one that we implement in schools. And the reason it's simplified like this is we're working with young children. We were working with grade 3 through to grade 6, and to have a 4-section framework was easy enough to sort of say, well, where are we? What are we doing in relation to this framework? And the young children could follow the framework. So, of course, most statistical inquiries start off with a question. We want to answer a question. We go and we want to be able to go and collect data to answer that question. We want to analyse the data, and then we want to interpret the results. And when we interpret the results, we want to position our thinking back into what the question was in the first place so that we're actually answering the question. So over the period of a 4-year project, we've implemented this as a framework for children to work with in schools. So it's a pedagogical framework in a sense that it's an inquiry framework. It has separate steps that you can work through for a statistical inquiry. And we've found it quite successful with young children to get them to thinking about what they're doing with data at different stages. And hopefully we're sort of setting them up for the future in a sense that they know the work of a statistician, that they know it's important that we need to start with a question and ask ourselves, what data do we need to answer that question? How might we analyse the data, and what do the results mean? So underpinning that practice, so that's just a pedagogical framework. So we've got these concepts, these big ideas of statistics. And when we start analysing data and doing different things with data, then we've got distribution, variation, expectation, randomness, and informal inference. So when we look at variation, we want to know what's different, what's changed. We need to compare data, things like that. Expectation is, what do we expect from the data? Randomness, what sort of patterns are coming out of the data? Informal inference, and this is different than formal inference. So when we're talking about tertiary education and statistics, you start moving towards using p-values and confidence intervals and things like that. In primary school, we talk about informal inference, and that's just qualitative statements that we can make from the data. That when we look at the data tells us a story. So we can talk about being confident and about our results. And we can talk about the distribution, how the data are spread out, those sorts of things. So these are the underpinning key concepts that we look at with classroom statistics. And we don't necessarily use these terms with young children, though in our project, variation was the underpinning concept that we were looking at with students. And of course, what we did was that we wanted the students to use the word variation. So we used to talk about the big V word, and you'd sort of start a conversation with the students and sort of say, what's the big V word? And they'd all sit there and say variation. So we set it up so that they were thinking that this sort of thing that we wanted them to look at as well. So we're sort of setting up for what we're looking at. Now, even though variation was a key component of what we looked at in the classroom, we do acknowledge that some of the activities there's distribution in there, there's randomness in there, expectation and so on. But our key idea and what we analysed and what we looked at was variation. So these are key concepts, and what we're looking at now is a conceptual framework that we could describe. But when we start talking about research and what we're doing for research, we want to be thinking about the theoretical perspectives. So I just sort of wanted to just step through some of the things that happened with our project and talk about some of the considerations that we had along the way that both pushed the direction of the research, but also caused us problems along the way. And so we'll talk about that. So we work with grades 3 to 6. You know, they do, you know, young primary students. We do qualitative research mostly. I mean, we do some, we don't necessarily do statistical analysis in terms of giving surveys and that sort of thing with young children. We want to look at what are they doing, why are they doing it, and that sort of thing, what influences what they do. So we had a project called Modelling with Data, Advancing STEM in the Primary Curriculum. And my partners were Professor Jane Watson, which I'm hoping most of you have sort of come across that name. Jane's a very experienced researcher in statistics education. And the other lady was Professor Lynn English from QUT. So Jane Watson is at the University of Tasmania in Australia, and Lynn English is at Queensland University of Technology. So we had a 4-year longitudinal study, and we had 2 schools, one school in Hobart and one school in Brisbane, because Lynn English was based in Brisbane and Jane and I were based in Hobart. So we sort of had 2 regional aspects. There was, at no time did we try and compare groups. They weren't interested in whether Hobart students did better than Brisbane students or not. And it just wasn't practical for that sort of thing. So it wasn't as if we did any randomisation or anything like that. So the project was thinking about what sort of activities could we do that were in STEM education, so science, technology, engineering, mathematics, that gave us data that students could work with. And that was a big challenge, to actually come up with activities that were suitable for those disciplines that actually generated data that young children could work with. Because we really wanted it to be hands-on. We wanted students to generate their own data, to make it meaningful for them. And that was one of our first challenges. So if we think about research, you know, we want our research to be grounded in theory. We want to be able to explain what happens in the classroom. We want to explain why students do things in a certain way. We want to be able to talk about the development of their ideas, their cognitive development, those sorts of things. So we have theory that underpins what we do. And theory gives us a way of talking about things and generalising ideas across different samples. So I can work with a grade 3 class in Hobart, but what I'm hoping is that we generate some theoretical perspectives that can be applied and looked at in different contexts, that doesn't have to be dependent on somebody being somewhere in a certain place at a certain time. So what we do is we take our results and we think about them from a theoretical perspective. To do that, we use theoretical frameworks. And just like the one I showed you with the big ideas of statistics, it's a conceptual framework. It's a framework that names up different sections. But from a theory perspective, so the theory is just what, you know, that we use to make sense of things. That the theoretical frameworks are the ways that we look at things. And that gives us a way of thinking about what we're doing. So we look at, when it says there, provide the lens through which data are examined and analysed and interpreted and discussed. So we're looking at things through the lens of variation. The theoretical perspective that we had, we have to be thinking about, well, how do we think people exist in the world, and how are they, you know, how are they being in the world? So, you know, my perspective is that participation in the world is part of that everybody can participate, but they take away their own ideas about what happens, and they interpret their own ideas from what happens. So everybody has their own reality. They might have a common experience with somebody, but what each person takes away from that experience might be a little bit different. So to me, that idea that there's a reality, everybody has their own reality, and that's something that underpins what I do. And to go with that, I have this idea about how we learn, and I have a constructivist point of view for how we learn, that we put ideas together for ourselves. We take ideas, new ideas, and we meld them together with old ideas, and we come up perhaps with different ways of thinking, and maybe we build on our thinking. So if I have that theoretical perspective to learning, then what sort of frameworks and theoretical frameworks support my research? There are different theories that underpin education. There are behaviourist theories and constructivist theories and that sort of thing. So there's lots of ideas out there, and what you've got to think about is, well, what suits my way of thinking and what I think occurs, and then you can actually use that as a foundation for the way you choose a project and how you write a project up. So there are different paradigms. So, you know, my perspective with the project that we had, the modelling with data project, we had a pragmatic approach because we wanted to use particular research tools. We wanted to use software called Tinkerplots. We wanted to be able to get students to do certain activities and work in certain ways. So we took a pragmatist approach. It wasn't a grounded theory approach where we just waited for things to happen and we looked at what was occurring. We orchestrated things. We were purposeful in what we got students to do. We were purposeful in the way we analysed the data and those sorts of things. So we took a pragmatic approach. But there's many other valid approaches to take. You know, the positivist is more quantitative. Interpretivist is qualitative and has lots of interviews and observations, and transformative, that tends to be more to do with social issues and things like that, about how we treat other people and that sort of thing. Now, most of these paradigms can use qualitative or quantitative methods, but you need to be able to justify them. And the way we justify our choices is based on those theoretical perspectives about what we think about how people learn and what people do. And we go from that base. So our basic underpinning of things was a constructivist point of view that talked about that, you know, backs up the idea that we make sense of things for ourselves. Then we take we think from a learning perspective, an inquiry process is appropriate. So the practice of statistics is an inquiry process that we implemented. So there's some synergy between the series that we choose and the frameworks and structures that we use. And the pragmatist approach, we can justify things like choosing to use the software Tinkerplots, and not necessarily, you know, the alternative might be that you give students a choice of tools to use and they choose which one they use. But when you're a pragmatist, you want to say, well, you know, I really want to see what they want to do, what they can do with Tinkerplots. So that's what we give them. So our choices with research, you know, can be sort of grounded in these theoretical perspectives and the methods that we choose. So when we started the project, we had this idea of it being a design-based methodology. We wanted to be able to go in with grade 3 students, run an activity, analyse that activity, see what results we got from it, use that feedback, put it into the next activity, into the design of the next activity. So we had this idea that we were going to have this developmental process that allowed us to design something, analyse, redesign, and put it back through a cyclical approach. So design-based methodology is a framework that you can use to structure your research project. But as it turned out, it was a nice idea, but it didn't really work for us. And there was a few reasons why that does. And because it didn't work for us, we have really struggled to find that theoretical perspective that frames our research overall. And it's something we're sort of still wrangling with, because everything was sorted out, everything was organised in the first instance to be design-based methodology, but because we couldn't implement a cyclical developmental approach to what we did, then it sort of fell apart. But that doesn't mean that what we did wasn't good. We have theoretical underpinning for all the elements of what we've done in the project, but it just doesn't come together in a cohesive way as to what it would have been desirable from what we wanted to do in the first instance. So when you look at design-based research, this isn't a map of the project. This is a map that I had from my thesis, my research, my PhD thesis. This is the map of a design-based research inquiry, and there's lots of different sections and there's lots of different elements to it, and it's very complex. So unless you get your design right, then you can't map out in this way. And that's what we've found with the current project, the Modelling with Data project. We couldn't map out the developmental process that we had adopted and implemented throughout. So we've been left in a situation where we haven't got that overarching theoretical framework that we can describe for the whole project, but we've certainly used some strong theoretical framework works for elements of the project. So I just wanted to just raise the point that design-based research is complex. It does need to be cyclical and iterative. It does need to inform theory or develop new theories, and it happens over a long period of time. So, so a little bit like action research, you really need to make sure you've got time to analyse data and to make some adjustments based on that analysis and then implement new strategies again. And we just didn't have the time to do that with the project. So when we start thinking about the practice of statistics in our project, because it was money that was funded because it was part of a STEM project, then we had to make sure that we had STEM learning contexts. So it wasn't just a matter of giving the students data and telling them to do something with it. We wanted to actually embed those things with it across the curriculum. We mostly focused on the science curriculum. We did involve some technology in using Tinker plots, and we did have a couple of activities that followed the engineering design process, which is in the diagram that you'll see there. And the engineering design process fits really nicely with this practice of statistics, because when you design and make something, you've usually got a question or a problem that you want to solve. You know, people want a new can opener, so that's the problem. So then you make a plan about what you might do. And same way, you know, if you make a plan about making a can opener, you want to be able to test it and see if it works properly, see if it works consistently, see if you change things, whether or not it works differently. So the idea that we can plan, we can collect data, analyse data, and when we get to interpreting the results and drawing conclusions, with engineering, you might make some adjustments and go back and test again, make a new plan and collect more data. And that's the same in statistics. Often we get to the end of a statistical project, we pose a question, we collect some data and we find an answer to that question. Often more questions arise. And when more questions arise, we need to plan to collect more data and to be able to answer the question. So it can be very cyclical and ongoing. It's not necessarily, the practice of statistics is not necessarily one iteration of the process only, that we can go back and do different things. And we did do that with the students. We chose activities where they collected some data at one stage, made some adjustments, and then collected the data again. So again, most of what we did, what we were looking for in students' work was variation, even though we do acknowledge that there was lots of other statistical ideas expressed as well. So we chose the software Tinkerplots. Let's see if this is going to work. So Tinkerplots is software which has a drag and drop functionality. So it's great for young children because they don't need to program, they don't need to write things into cells. It does have a function where you can put data into cells and represent it in a graph, but essentially you can get them to import the data and then they can just click and drag, just like you can see in front of you now. You click on an icon and you can drag it and you can do different things. You can randomize it back to that and then you can start dragging and sorting. So this ability to sort and group and cluster and all those sorts of things, it really is great for young children to be able to ask themselves, what is the best representation that answers my research question? So, excuse me, just for 1 minute. All right, sorry about that. So Tinkerplots is a commercial product and you have to pay for that for schools, for students to use it. But there is a new web-based data analysis system, which is similar to this, but a little bit more complex, and it's called CODAP. So it has that same sort of idea of being interactive and taking on the idea that looking at data, you can explore data in different ways and look at different things. So we didn't use this for all activities. In the first year of the project in year 3, we didn't use Tinkerplots, but we did use it most of the time from then on. Okay. Okay. So well, the first activity we did was manufacturing licorice. So the idea was that students had to make licorice by hand and by machine. So you can see the students there pushing the Play-Doh out of the Play-Doh extruder and also making and weighing handmade licorice. And this was a great activity for them to start off with, just the idea that when we make things by hand, some things can be really big and some things can be really small, but if we make them by machine, then things are more consistent. And we had those conversations with the students about why when you buy a packet of licorice, nearly every piece is the same. Why is it that when you make something homemade, that things are not always exactly the same? So we got students to make some handmade licorice pieces, and they had to be 8 centimetres long and 1 centimetre in diameter. And the green graph in front of you, you'll see that the data are spread out quite a bit. So they're the handmade ones. So, and the red ones, that's machine made ones. So we had this conversation about the spread, the range. With this particular activity, the measures of centre are the same for both situations. And the idea starting off with this was to actually just be able to get students to recognise that there is variation, that things are different, and when you do things with 2 different treatments, you won't necessarily get the same results, but you can compare results and you can talk about that. So they can talk about which ones are the biggest, and how much bigger one is than the other, and those sorts of things. So we started off just trying to give them the tools for talking about data and using data. And working with year 3 students, the idea was that we didn't throw them into using Tinkerplots or anything like that straight away. We wanted them to support their graphical construction skills. So for this activity, we used sticky notes. So each student put the mass of their licorice pieces onto a sticky note, and the sticky notes went onto the board with the scale that we've got. And when you've got the scale the same for both treatments, then you can compare them directly. You can compare them and sort of say which one, well, where is the measure of centre, which one has the largest, which one has the smallest, those sorts of things. So you can have, there's lots of conversations you can have with young children about data to actually get them thinking about, well, what is it that statistics is about? And essentially statistics is about variation, about looking for differences and being able to compare things. And when we start talking about the mean and average and those sorts of things, then we're actually comparing. Next activity we did was the heat is on. So this activity, students sort of measured the heat of water as it decreased when it was in hot water. We started with hot water and it went down over time, and the students measured and recorded over time. So one cup had insulation around it. So we used a polystyrene cup around the other cup. So we had 2 different treatments. And again, we supported the students with the graphical construction skills because they put their data points onto a large graph sitting in the room. And so they added their data to this. So what you see there is the construction of a set of data from a class. So once we had this, we're able to talk about, well, what's happening with the hot water in the cup that's not insulated, what's happening with the water in the cup that is insulated, and what's happening with the water that's in the tray. And that's the black line at the bottom, that's the water in the tray. We put some iced water in the tray and we could monitor that as well. Now, what we realised when we ran this was that this activity didn't follow on from the last one, which we were able to compare centres. But we were driven by the Australian curriculum. And in year 3, it says you have to do heat, and and then in year 4, you do force, and in year 5, you do chemistry with concepts of chemistry. So it's really difficult to be thinking about, well, what sort of activities fit the curriculum, but also fit this idea of being able to have data activities that are suitable for young children. So after year 3, we did an activity was posing questions. So we wanted the students to pose questions. So thinking about that practice of statistics, we just didn't just want, in the first couple of activities, we posed the question, we still went through that inquiry process of posing a question, collecting data and so on. But the researchers posed the question and the students collected the data. So we wanted to give students the experience of posing their own questions. And that proved to be very difficult. And it's my contention that that is the most difficult part of the statistical inquiry, is coming up with that statistical question that requires data to be answered. You can ask lots of questions, but they're not necessarily statistical questions. And then, how you phrase the question will depend on what data gets collected. And again, that's difficult. But it's really interesting the sorts of things that students do with the data. It was all about the differences between Hobart and Brisbane. So students sort of ask questions like, how long does it take you to go to school? How much homework do you do? What sort of food does your family eat, and things like that. So that was all, it was student generated. So the students posed the questions. We got them to talk about the questions, and we got them to modify the questions so that the ones they asked originally were statistical questions that could be answered with data. So we had to work with that. But like I say, I still think this is one of the most difficult parts of the practice of statistics, is just posing that initial question. But when they come to hand drawing their own graphical representations, you'll see there's just a huge variety of things that students will do. But the important thing is that whatever the students draw, they can make sense of. So the one with the buses and the trucks, with the number of people in the buses and the trucks, is related to how people get to school. So there's cars and there's buses and there's trains. And so there's so many people that come by bus and so many people who walk and so on. So it makes sense to the students. So that's a graphical representation that they felt made sense of the data. And yet some students were able to draw what we consider to be a conventional graph with a scale and all the rest of it. And that is their interpretation of the data. And even somebody writing something in words rather than using a graphical representation, just putting things into those boxes, Brisbane, Hobart, they're making sense of things and sorting things and categorizing things, as well as using numerical values to explain the data. If you talk to each of the students who created these, they will be able to make sense of it for themselves. And we did an activity of catapults. So we sort of realised later that this activity should have followed the licorice activity, because the licorice activity had two different conditions, but the same measures of centre, because they were sort of targeting a certain size and a certain shape, then the mass was going to be, the measure of centre is going to be the same. But this activity, the measure of centre is different. So we ran the catapults. So we had these devices made and students put ping pong balls on the spoon. You pull the spoon back and let it go, and you measure how far it goes. So the graph there at the top there is the data from one group, and the one at the bottom is the data from the class. So this idea that we're just building on this idea that if we get a small amount of data, it might tell us something, but if we get more data, we might get more information. So we can talk about what's typical performance. So when you put all the data together, you're actually got a stronger case for saying something is working in a certain way. So we can talk about how far the catapults might go. We can talk about how much variation there is in the distance that the balls go. And then you start talking about the students, well, why do you think the results are the way they are? And they'll start drawing on the context and sort of say, oh, it's the way I'll let the spoon go, and things like that. So they can appreciate when they get a value that's nowhere near anybody else's, that maybe there was a mechanical problem that interfered with it. So they start getting the idea that there's context and things that influence data. And sometimes there's data that we don't need to count because it doesn't fit with everything else. But then we tightened the string and we did some more trials. And when we did more trials, it was really nice. It came out that the second set of trials, which is in orange at the bottom here, the second set of trials, the ball went further, but it was less consistent. It was more spread out. The data were distributed far more than what it was when the first set of trials. The catapults tended to be more consistent, and yet when we did the second set of trials, it went further, but there was more variation. So we had that conversation. Well, if you're storming a castle and you had a device, a trebuchet, that you wanted to throw missiles into a castle, where would you put the trebuchet based on your data? How far away would be the best place? If you put it close, if you might, so if you put it in a certain place, then it might be inconsistent. You might not hit your target, but if you do something else, you might hit your target. So use your data to make those decisions. And that's what we're trying to sort of work with students to say that, if we have data, we can use it to make meaningful decisions. And we did another activity on viscosity, and this one came later, and the choice of topics was based on the curriculum, that we were forced by the science curriculum to do certain activities in certain years. And in this activity, the mystery concentration, we sort of did interpolation. So being able to collect some data, just like a chemist would, collect some data and run some tests, and then you run an unknown sample and you compare your unknown sample with your other tests, and you come up with the concentration of your sample. So we did this sort of thing with students. So they had, we used hair conditioner. We found that worked well on plastic and let it drip down. So, and then we sort of how far to go down at a certain time. So they're able to do that. And young children are very able of looking at the data and making predictions and using trend lines. At this age, we didn't force a linear trend line on them or anything like that. Tinkerplots has a really nice function where you can just use a drawing pencil and put your trend line in for yourself. So we're not forcing that idea that they have to have a straight edge to work, to put in a trend, that they can actually think about the trend in the data. And sometimes the trend isn't always linear, but we tend to only give, when we start talking about lines of best fit, we tend to only give students examples that do have a linear function as a line of best fit, and start talking about the idea of where's the middle of the data and those sorts of things. And then we did another activity with the viscosity idea, and the same in terms of lava flow and being able to predict, you know, if we measure the lava flow up to 6 intervals, can we make predictions for interval 10? You know, where's the lava going to be in the future? And these are the sorts of things that scientists do. They make predictions based on data we've collected historically, and we make predictions about what it might look like for the future. So it's really nice. So in Tinkerplots, you've got this drawing tool that you can use, and it's really, I love this example because you've got a student who says that these data here, is Mark them off and said they're outliners. And it's really interesting because we call them outliers, but the students sort of picked up on that and sort of said, called them outliners. Sometimes students do quirky things, and it's really nice to sort of encourage that sort of thing. As you know, it obviously picked up on this idea that there's data that doesn't fit with the rest of the data, so what do we do with it? Another activity was seed dispersal. So we got the students to make these devices, that the idea that seeds get dispersed by 3 different methods, in a sense that they have kites and spinners and sails, those sorts of things. So we call them, you know, sails, parachutes and helicopters. So they made these devices. We set up some fans and we dropped the devices and measured how far they flew into the room from the fan. It was a very successful activity. And this is the one that we use the design process, you know, the engineering design process for. So they made their device and then they adapted it and changed it and trialed it again, and we asked them, did they improve it or not? So they had to make some decisions based on the 2 sets of data, saying whether or not they had improved the performance of their device or not. And we just gave them lots of heaps of bits and pieces and things, and they just made them, and it was a really successful activity. And so from a data perspective, we got them to compare and which one was better. So the sail, the parachute and the helicopter. And of course, the different devices depend, the way that seeds work, it depends on how far they go from the tree. So different devices. So which one is the best if you want to take it furthest from the tree, which is the best device if you don't want it to go very far. So we can sort of think about that from the data. So we've got students to use Tinkerplots again for those sorts of things. Another one we did was how do plants grow best? Now, this activity was designed so that students had some choice. Up until this stage, we had told the students what to do in a sense that we set up the experiment and they ran the experiment. But in this, they sort of made some decisions. They could plant their seeds in different types of soils. They could choose which seeds they could plant, and then they could choose how they water those plants or what nutrients they use for those plants. So some plants were fed vinegar, different concentrations of vinegar. Some plants were fed water, sugar, so different concentrations of sugar and those sorts of things. And you'll see all those plants there in the image there are radishes, and yet you can see there's different sorts of leaves for each one. And of course, so you can see that the different conditions and the different concentrations of whatever choices were made were impacting on the plants. And that sort of came through in the data because they measured the growth of the plants over a period, quite, 3 weeks that we did it for, growing the plants. And they could choose whether or not they grew wheat or radishes. And it was really interesting I sort of thought in the very beginning, I thought, oh, the kids will find this boring. They won't like it. And they engage with it so well. They had to measure the plants every day. We weren't there. We just sort of said, you need to measure your plants every day. And they did. They measured the plants and they recorded them. And they were really engaged. And I had one student come up to me and said, oh, I've never planted any seeds before. And I was just personally astounded. I never thought that people didn't do those sorts of things. I live in a country area, so to have a child say to me, oh, I don't do anything in the garden, I don't plant anything, I've never planted anything. And I said, well, it made me realise that sometimes we make some assumptions about what people can do and what they can't do, and what they might enjoy. And it was a great activity. So anytime you get a chance to grow things with young students, it's really worthwhile. But again, we sort of got them to look at the treatments and to decide which treatment was best. So we had these different trials and different treatments. So then they had to think about, well, which one was best. And we start talking about being consistent and things like that. We also did a mystery spinner activity. Now it was only possible because of Tinkerplots, what Tinkerplots can do. So we all know regular spinners, we flick the spinner thing and lands on somewhere, we record the data, we do it lots and lots of times. But the thing is with Tinkerplots, you've got that opportunity to actually run the spinner lots and lots and lots of times. So young children, by this stage they're in grade 6, and you give them a 4-part spinner, they know it's a quarter, they can tell you that. They don't need to run any trials to tell you that it's 25% time would be green and so on. So we wanted to see whether or not they could make predictions about the spinner from the data. So we had this mystery spinner and we set it up, and all they could say was just this blank thing, but they could run it. So they could repeat this experiment 20 times. We got them to run it 20 times, 50 times, 100 times, 1,000 times, and then we could actually run it up to 10,000 times with Tinkerplots. So, the more and more we do this, the closer the results get to the theoretical values of the theoretical probability of the spinner. So being able to do that with Tinkerplots has really been useful. So then we could reveal what the spinner looked like. And we didn't choose the even parts because we didn't want children just making predictions from just their previous experience with spinners. We wanted them to really challenge them. And so we gave them different weighted parts of the spinner. And this activity was to sort of start talking about how confident they were with this data. How could you tell that you had the right mix? At every stage that we got them to do 20, and then we got them to do 50, at each stage we got them to predict what their spinner would look like, and we got them to draw what they thought the spinner looked like. And at each stage we asked them about how confident they were. And it was just really interesting because when they did a few trials, they said, yeah, I'm confident, it's 30% red and 40% blue and so on. And then they'd do a few more trials, they'd do a few more goes, and then they'd become less confident. So the more data they got less confident, but I think they were less confident in their initial prediction, not necessarily less confident from the data. And then once we did lots and lots more, they became very confident. So just this building in this idea that sometimes it's a really good thing if we get more data and we can be more confident with what we do. We didn't do it from a sampling perspective, but just this idea that we can, if we do more with an experimental spinner, the more trials we do, the closer we're going to get to that theoretical perspective that we can calculate from later on. So I said before, we didn't really have that overarching theoretical perspective that we wanted to from the very beginning, but we did use theoretical perspective and theoretical models to guide what we do. We use the practice of statistics, we use the engineering design process, and we use the big ideas of statistics. They're all conceptual and pedagogical frameworks that we can use. But when we came to analysing the data, most of the time, most of the analysis was done using the solo model. So this solo model is developed by John Biggs and Collis. I'm not sure of his first name. I know John, that's why I remember his name. Biggs and Collis. And the work's been around for a long time, and it's been applied a great deal in tertiary education, but it's very, very suitable for young children to be thinking about it in these ways. So it's a developmental model. It's based on cognitive psychology, and the idea at the very basic level, it's pre-structural. So, you know, the response is unrelated to the question, not idiosyncratic. So, you know, if you ask the students, what is, you know, you're looking at a graph and you sort of say, what is the most common data point, or something like that? And they say, oh, elephants. Well, the most common, you know, the graph might be about fruit they had for school, but they might just say elephants because elephants eat the fruit they like, or something like that. When the young children really say some really odd things that are pre-structural, they've got nothing, they're not statistical. Their response is not statistical, and it's sometimes not related to what you're actually doing. And sometimes they're just, the ideas are just a bit too simple to be able to be coded. Unistructural, they start talking about one thing. So they're talking, you know, they'll be able to say, oh, you know, 59 is the most frequent. You know, the median is something. So it's just one thing, it's one way. But multistructural, they start bringing things together. You know, so multistructural might be that they start being able to draw graphical representations that have two axes rather than one axis, and that sort of thing, and start looking at putting ideas that way. And when it's relational, they can really start talking about things that are connected to and can be influenced in different ways. So they might be able to, with the mystery activity, they might be able to talk about the concentration from the data, not just talking about, oh, number 5 is 52. You know, when I did experiment 6, the answer was 110. So they start connecting things together more across that way. So the silo model gave us a theoretical perspective of being able to look at the student's level of understanding, and it's incremental and developmental across these levels. And there's a lot more work about that I won't explain here. If you're interested in looking at a solo model for anything, Randall Groth's done a lot of work with that as well, and Jane and I have written up papers using the solo model in different ways to what's here. But this is the fundamental part of it, that, you know, pre-structural doesn't answer a question, or it's a non-statistical answer. Unistructural, they start talking about one aspect of a graph. Multistructural, they mention a couple of different things about the graph. And relational, they start connecting things together and start talking about causes and influences and that sort of thing. So we did have that theoretical background to the way we analysed the data. And the other thing that we were going to do was, well, when we started out, we had this idea of design-based process, and that we were going to have this long-term longitudinal study. So we were going to look at progress and development over time. But what we came to realise was that the activities that we chose, because of the curriculum, didn't give us that developmental notion across time that we were going to be looking for, because we jumped back and forth from different ideas, and the complexity of the ideas didn't flow and weren't developmental. We didn't introduce things in a developmental way, which is what we intended in the first place, but it just didn't work that way. So we've got some really good results, and at the moment we also did survey the students in the beginning and at the end of every year. And at the moment, we are analysing that data using rash analysis to see if there's anything that we can sort of come up with this idea of a development process with the students. But that isn't at a stage where I can say that we've been successful in doing that. So we did find it challenging choosing contexts for the fit of the school curriculum. We did find it challenging to find science activities that allowed us to collect data. There's a lot of science resources out there. There's a lot of activities that students do in science, but they're not necessarily good ones for collecting data. So we sort of had to think about how we could do that. But, you know, even though the project wasn't implemented in the way we wanted it to, we still consider that the project was a success because the students did a lot and we learnt a lot. We learnt a heck of a lot from the students about how they learn and use statistics in primary school. So I'm hoping you found that interesting. And there's lots of references there that you can look at. And if you're interested in any of the papers that we've written up on the project, if you look me up on ResearchGate, you'll be able to see the whole range of things that we've done.